Well, welcome back to our course, Networks and Distributed Systems, based on a textbook by Jim Caros and Keith Ross, Computer Networking, a Top-Down Approach. For the last few lessons, we have been examining the network layer of the TCP/IP model. In our most recent lessons, we were discussing link state routing and distance vector routing. Now we're going to move on to another topic, hierarchical routing. So let's get started and pick up where we left off. In our study of link state and distant vector algorithms, we viewed the network simply as a collection of interconnected routers. One router was indistinguishable from another in the sense that all routers executed the same routing algorithm to compute routing paths along the entire network. In the real world, a set of routers all executing the same routing algorithm is just a little bit simplistic for at least two important reasons. Scale becomes a problem. As the number of routers becomes large, the overhead involved in the computing, storing, and communicating routing information, such as link state updates or least cost path changes, becomes prohibitive. The Internet consists of hundreds of millions of hosts. Storing routing information at each of these hosts would clearly require enormous amounts of memory. The overhead required to broadcast link state updates among all routers in the public Internet would be too much of a load on bandwidth. A distance vector algorithm that iterated among such a large number of routers would never converge. Clearly, something must be done to reduce the complexity of route computation in networks as large as the public Internet. Also, administrative autonomy is another issue. Although researchers tend to ignore issues such as a company's desire to run its routers the way it pleases, there are important considerations. For example, a company expects to run whatever routing algorithm it chooses, or to hide aspects of its network's internal arrangement from outside entities. Any organization should be able to run and administer its network as it wishes, while still being able to connect its network to other outside networks. Both problems can be solved by organizing routers into autonomous systems, with each autonomous system consisting of a group of routers that are typically under the same administrative control. Routers within the same administrative control all run the same routing algorithm and have information about each other. The routing algorithm running within an autonomous system is called an intra-autonomous system routing protocol. It's necessary, of course, to connect autonomous systems to each other. So one or more of the routers in an autonomous system will have the added task of being responsible for forwarding packets to destination outside the autonomous system. These routers are called gateway routers. The figure you see on your screen provides a simple example of three autonomous systems, AS1, AS2, and AS3. In this figure, the heavy lines represent direct link connections between pairs of routers. The thinner lines hanging from the routers represent subnets that are directly connected to the routers. Autonomous System 1 has four routers, 1A, 1B, 1C, and 1D, which run the intra-autonomous system routing protocol used within Autonomous System 1. Each of these four routers knows how to forward packets along the optimal path to any destination within AS1. Autonomous routers AS2 and AS3 also each have three routers. Note that the intra autonomous system routing protocols running in AS1, AS2, and AS3 do not have to be the same. Also note that the routers 1B, 1C, 2A, and 3A are all gateway routers. It should now be clear how the routers in an autonomous system determine routing paths for source-destination pairs that are internal to the autonomous system. But there's still a big missing piece to the end-to-end routing puzzle. How does a router with some autonomous system know how to route a packet to a destination that is outside the autonomous system? It's easy to answer this question if the autonomous system has only one gateway router that connects to only one other autonomous system. In this case, because the autonomous system's intra-autonomous system routing algorithm has determined the least cost path from each internal router to the gateway router, each internal router knows how it should forward the packet. In this case, because the autonomous system's intra-autonomous system routing algorithm has determined the least cost path from each internal router to the gateway router, each internal router knows how it should forward the packet. The gateway router, upon receiving the packet, forwards the packet on the one link that leads outside the autonomous system. The autonomous system on the other side of the link then takes over the responsibility of routing the packets to its ultimate destination. As an example, suppose router 2B in this figure receives a packet whose destination is outside of autonomous system 2. Router 2B will then forward the packet to either router 2A or router 2C as specified by router 2B's forwarding table, which was configured by Autonomous System 2 or AS2's intra-autonomous system routing protocol. The packet will eventually arrive to the gateway router 2A, which will force the packet to 2B. Once the packet has left 2A, AS2's job is done with this one packet. So the problem is easy when the source autonomous system has only one link that leads outside the autonomous system. But what if the source autonomous system has two or more links through two or more gateway routers that lead outside the autonomous system? Then the problem of knowing where to forward the packet becomes significantly more challenging. For example, consider the router in AS1 and suppose it receives a packet whose destination is outside the autonomous system. The router should clearly forward the packet to one of its two gateway routers, 1B or 1C. But which one? To solve this problem, AS1 needs, first, to learn which destinations are reachable via AS2 and which destinations are reachable via AS3. Second, to propagate this reachability information to all routers within AS1 so that each router can configure its forwarding table to handle external autonomous system destinations. These two tasks, obtaining reachability information from neighboring autonomous systems and propagating the reachability information to all routers internal to the autonomous system, are handled by the Inter-Autonomous System Routing Protocol. Since the Inter-Autonomous Routing Protocol involves communication between autonomous systems, the two communicating autonomous systems must run the same Inter-Autonomous System Routing Protocol. In fact, in the Internet, all autonomous systems run the same Inter-Autonomous System Protocol, called BGP4, Border Gate Protocol 4. As shown in this figure, each router receives information from the intra-autonomous routing protocol and an inter-autonomous routing protocol and uses the information from both protocols to configure its forwarding table. As an example, consider subnet X. And suppose that Autonomous System 1 learns from the Inter-Autonomous System Routing Protocol that subnet X is reachable from AS3 but is not reachable from AS2. AS1 then propagates this information to all of its routers. When router 1D learns that subnet X is reachable from AS3, which is reached from gateway 1C, it then determines from the information provided by the intra-autonomous system routing protocol the router interface that is the least cost path from 1D to gateway router 1C. Say this is interface I. The router 1D can then put the entry into its forwarding table. Following up on the previous example, now suppose that AS2 and AS3 connect to other autonomous systems which are not shown in the diagram. Also suppose that AS1 learns from the Inter-Autonomous System Routing Protocol that subnet X is reachable from both AS2 via gateway 1B and from AS3 via gateway 1C. Autonomous System 1 would then propagate this information to all its routers, including router 1D. In order to configure its forwarding table, router 1D would have to determine to which gateway router, 1B or 1C, it should direct its packets that are destined for subnet X. One approach, which is often employed in practice, is to use hot potato routing. That's a real technical sounding name, hot potato routing. In hot potato routing, the autonomous system gets rid of the packet, the hot potato, as quickly as possible. This is done by having a router send the packet to the gateway router that has the smallest router to gateway cost among all gateways with a path to the destination. In the context of the current example, hot potato routing running in 1D would use information from the intra-autonomous system routing protocol to determine the path cost to 1B and 1C, and then choose the path with the least cost. Once this path is chosen, router 1D adds an entry for subnet X in its forwarding table. This figure summarizes the actions taken at the router 1D for adding the new entry for X to the forwarding table. When an autonomous system learns about a destination from a neighboring autonomous system, the autonomous system can advertise this routing information to some of its other neighboring autonomous systems. For example, suppose that AS1 learns from AS2 that subnet X is reachable via AS2. AS1 could then tell AS3 that X is reachable via AS1. In this manner, if AS3 needs to route a packet destined for X, AS3 would forward the packet to AS1, which would in turn forward the packet to AS2. As we'll see in our discussion of BGP, an autonomous system has quite a bit of flexibility in deciding which destination it advertises to its neighboring autonomous systems. This is a policy decision, typically depending more on economic issues than on technical issues. You remember from our earlier lessons that the Internet consists of a hierarchy of interconnected ISPs. So what is the relationship between the internet service providers and autonomous systems? You might think that routers in an ISP and the links that interconnect them constitute a single autonomous system. Although this is often the case, many ISPs partition their network into multiple autonomous systems. For example, some Tier 1 ISPs use one autonomous system for their entire network, and others break up their ISPs into tens of interconnected autonomous systems. In summary, the problems of scale and administrative authority are solved by defining autonomous systems. Within an autonomous system, all routers run the same intra-autonomous system routing protocol. Among themselves, the autonomous systems run the same inter-autonomous system routing protocol. The problem of scale is solved because an intra-autonomous system router need only to know about the routers within its own autonomous system. The problem of administrative authority is solved since an organization can run whatever intra-autonomous system routing protocol it wants. However, each pair of connected autonomous systems need to run the same inter-autonomous system routing protocol to exchange reachability information. Next, we're going to examine two intra-autonomous system routing protocols, RIP and OSPF, and the inter-autonomous system routing protocol, BGP, that are all used in today's internet. These case studies will nicely round out our study of hierarchical routing. I think this is a good place to take a break. So go ahead and look over your notes, update your study guide, and when you're ready, come on back and we'll start another lesson.